Okay, so this is going to be the data reduction video for the second lab. This is flow through a pipe. So let's look at the data reduction that we have to do. We want to look at the static pressure distribution that we had for all of our static ports along the length of our pipe. Then from that pressure plot that we just made, we want to look at the entrance length for each of the runs that we have. Then we're going to look at the velocity profile for each of the fan speeds. Actually, for this case, there's only one fan speed, but we varied the discharge for this. So for that, that's when we adjusted the height of the pitot tube. And then we want to look at the volumetric flow rate of our system as well. So I'm going to go to Matlab. I've already typed all of this out, so you can pause the video right now and basically type all of this in. So what I've done is I cleared my memory so we can clear out all of the variables over here and look at the script that we want to work on. Then I've specified some constants right here for this lab. So we're dealing with gravity, so I put that in, and the water viscosity, the water density, the air viscosity, air density, and then the pipe diameter. And take note of the units that I'm using here as well, and make sure that you're keeping them the same as me, or you're being consistent with whatever you use for your lab. Okay, then I'm converting to meters, so centimeters to meters and millimeters to meters. And then I'm going to initialize my array sizes. Okay, so for this, the first one is the head data. So I have h equals zeros of 15, 5, 4. And that's for our 15 taps that we had, our 5 discharge openings, and then our 4 fan speeds. So let's go to Excel. And then this is all my head data for the lab. So this first column, this is my axial position. So if I go to the spreadsheet that we had for the lab, what we see on the left here is our tap number, and then we have the axial position, which is that first column that you just saw. And this is in units of meters as well. So you'll see on this last one I put a 0. If you look at the spreadsheet, there's nothing with the 0. Basically that 0 is accounting for this part right here, this open tap. Okay, so for that, we don't care about that distance, so we just want the pressure reading, so I'm going to put that distance as a 0. Okay, so that's our 15. We have 15 taps that are highlighted right here. And then the 5, again, that's for the discharge opening, so we have 5. And then we had 4 runs, so we have 1, 2, 3, and 4 corresponding to the fan speed. So our goal is to sort all of this data out later on into here's run 1, here's run 2, here's run 3, and here's run 4 for all of that height data that we had from our manometer. Alright, next one is the static pressure for the pitot tube. And then we have the stagnation pressure for the pitot tube. So we had 14 radial positions and 5 discharge openings. Let's go to the Excel sheet, or not Excel, but the spreadsheet that you had. So we have 14 radial positions here from the center line at 0 millimeters. And then we have our 5 discharge settings up here. 1720 again, those reference the atmospheric pressure. And 14 and 19, those are for the stagnation and the static pressure. Okay, so let's go on from that now. Let's go back to Excel. Here we go. So 14, I think 14 is the static pressure. That's off the top of my head. You can check your lab and be sure. And then 19, that's going to be the stagnation pressure. So we have 14 taps. And then we're doing that for our 5 discharge openings. Okay, let's move on. Now we have the axial pressure head. So for this, basically, it's the same as this H variable up here. But this time, I'm going to discount the reference tab. So I'm going to take that last row out of here. So now, I'm basically taking all of this data that's highlighted. Okay, and then and we're gonna convert this later on to pressure instead of a head reading that we have in this line. So this is in the head was in centimeters of water, I believe, and for the pressure we need to convert that into pascals. Okay, then we have Q, and that's our volumetric flow rate. So for that, we only had one fan speed for that, and we had 5 discharge openings. So we have 5 discharge openings and 1 fan speed, and then that's going to be the same for the Reynolds number. Okay, moving on. I'm importing all of my data, so I have my pressure data, velocity data, and the entrance length data. So that's sheets 1, 2, and 3. Your entrance length data, remember, we're going to look at the velocity plot that we have, or sorry, the pressure distribution plot that we have, and we're going to get the entrance length data from that. So keep that in mind for now. So basically you might not be importing this part right now, but I already have that data, so I have that there. And then I'm specifying the sheet that I have all of this on. So the pressure data was on sheet 1, velocity was on sheet 2, and the entrance length data was on sheet 3. Okay, now we're going to sort the data into separate arrays. So for the position, for the axial position, that was on sheet 1. In the first column, rows 1 to 14. So x equals the axial position. We're on our first sheet here, so it's 1 to 14 for our rows here, and in this first column. Remember, this last row is just for the reference pressure, so we don't need that. The radial position, that was on sheet 2. Let me run this, and that'll make more sense. So I imported it onto the variable b here, so the radial position is on b. And for that, we're taking all of the rows in the first column. So all of the rows in this first column. And remember, in the lab, that was in units of millimeters from the center line. The discharge percentage, so that's on sheet 3 for me, or sheet C. Let's open that up, and that's in taking all the rows again in the first column. So we have 10 all the way up to 100%. And then we have our entrance length data. And we're going to non-dimensionalize this later on. So for me, that's on sheet 3 or C once again. And that's all of the rows for columns 2 to 5. So here we go, all of that. And again, we're going to go over the entrance length later on. Okay, so now what I've done is I've typed out this code right here to sort out the axial pressure for each of the runs. So I have for I equals 1 to 4 for each run. That's for the 4 fan speeds that we have. And then I have some kind of weird looking code here, so I'll go through this. So we want to start out for the first run. We want to get our data starting in column 2 here. So I have J1, just some variable. I have J1 equals 2 plus 5 times I minus 1. So remember, I want to start this data for the first run in column 2, and I want to go out to this column here. So I'm doing J1 equals 2 times 5 times I minus 1. So if we start out for the first run, I minus 1, that's 1 minus 1, that's 0. 2 plus 5 times 0, that's 2. So I'm basically telling Matlab I want to start in this column 2. Then I have J2, that's J1 plus 4. So now I'm saying I want to end my data collection starting from J1 and then go out 4 columns. So here's J1, and I go 1, 2, 3, 4. And now I'm telling Matlab to collect all of that data from J1 to J2. So now I'm doing from J1, that's in column 2, all the way to J2, that's basically this column here. And then in this case, I'm going and I'm collecting all of that data. So that's all of the data for the first run at the fan speed of 1250 RPM. And then this last line here, that's basically going to do what we just said for all of the 4 runs. So now, if I run my code, which didn't really have to do, but if we do that and then I open up the head data that I just made right there, we have all of that data that we just had. Okay, so let's look at this. So we have all of this data, that's all right here. And then we have, I think I grabbed 1 column too many, but whatever. Then we have all of this data, that's all right here. And then we have that for the 3rd run here, and then for the last run. So it's some pretty nifty code. Now it's from Dr. Mayerell. So don't thank me, thank him. It's pretty nice. Alright, so we're going to do the same kind of thing for the radial velocity pressure head right here. Okay, so now I've added this code right here for the radial velocity pressure head. And again, we're basically going to do the same as we just did for the axial pressure head. So I have for I equals 1 to 5, and again that's for the 5 discharge openings that we have. 10%, 30%, 50%, 70%, and 100%. Now, I'm going to start out with the static pressure, so that's H underscore stat. Tap 14, that's the static pressure, and tap 19, that's the stagnation pressure. So if we look at our data, for the first run, that's for the discharge opening at 10%, I want to start collecting my data in column 2 once again. So I have J equals 2. That first 2 right here, that's going to say that we at least start in this column 2. Then I'm going to do plus 2 times I minus 1. So let's pretend we're doing this for the first run. So then I have 2 plus 2 times 1 minus 1. So we have 2 plus 0, and that's just 2. So now we have H static pressure equals all of the rows for the first run, and then we're starting in column 2. So now I have that static pressure. The stagnation pressure, we have all of the runs for the first run, or we have all the rows, sorry. We have all the rows for the first run, and then we're doing that for the column J plus 1. So that's column 2 plus 1. Now we have this row for the stagnation pressure for the first run, which is what we want. Okay, so now we have all of this data, the static pressure here and the stagnation pressure here. And we're going to do that for all of the other runs, and then we can run the code. Let's go to the static pressure here. So we have the static pressure here, 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 and here. And you see, if you kind of looked at both of them at the same time, they match up. So what I've done now is question 1, the pressure distribution, really the static pressure distribution. So for this, we want to look at the static pressure for each tap. So that's from tap 1 to tap 14. Okay, so for this, we're going to use for loops once again. So we have for I equals 1 to 4 for the 4 fan speeds, for J equals 1 to 5 for the discharge percentages, and for K equals 1 to 14 for those 14 pressure taps. Okay, now I'm using a hydrostatic equation here, so just rho g h, where h is going to be our head difference for the reference tap that we had minus the specific tap that we're trying to look at. So let's think of it this way. If I want to find the static pressure for the first tap, we have rho times g, then we have times h of 15. So let's go to, and remember this is for our variable k for the pressure tap, so if I look at my h data though, I have h of 15. So this is all my head data, so it's all of this stuff here. Remember, we had 15 rows right here. So h of 15 is all of this data. So if I have h of 15, comma 1 for j, that's going to be for that first discharge percentage, and then I is going to be for the first run. So that would be this value right here. It would be 20 if I had h of 1, comma, or h of 15, comma 1, comma 1. I hope that made sense. So we're just doing, for the pressure tap, for the static pressure, rho times g times our height differential that we had from the manometer. Okay, so you can run that, and then you will get all of your pressure data. Again, we have them all separated into the 4 runs here. Okay, and if you're looking at this and you're like, well, why are these negative? That does not make sense. Remember that in this case, we were sucking the air into the system. So what we had was suction pressure, so that's why it's negative. Alright. Okay, so the second question that we have here is the entrance length. So for that, we have to normalize the entrance length by the diameter. Okay, so just like it says there. Well, we don't have the entrance length yet, right? So remember in class, we need to look at the plots that we have from the static pressure distribution, and then we can find the entrance length. So what I've done here is just made figure 1, and I've plotted the static pressure distribution for the first run. So that's this last one and all of these, comma 1, all at the end. And then I've made a plot for each of the discharge openings, so for 10%, 30, 50, 70, and 100. And we want to get all 14 taps, so that's why I have all of the rows in this first input right there. And that's taking all of this data that we just wrote out, or wrote our code for right here. Okay, and then we're plotting that with our axial position as well. So if we run this, then we get this plot. So we have the axial position here, and then our pressure in pascals on this axis. So I'm going to blow this up. And remember, to find the entrance length, we want to look at the plots. So remember what I said in class, we're kind of starting out somewhat linear in all of these plots. And on each of these, there's a point where the pressure really starts to drop off. So at a discharge opening of 10%, that's in blue here. Here we are, we're pretty steady or horizontal, and then there's a drop in pressure, which is what we expect as we move along the pipe here. And then we have a big drop in pressure at 4 meters. So it's really 4.1. You see we have x equals 4.1. So that's going to be the entrance length that we have right now, is 4.1. Then for 30%, we also have 4.1. 50%, it's going to be here, we have 3.1. And then for 70 and 100%, now we're out here before we drop off quite a lot. And we are at 1.1. So those are in meters. But remember, the entrance length should be dimensionless. It should be some length, which is what we just found, L sub E, that's usually what we have. I'll just leave this as L though. And that's going to be the entrance length once we divide this by the diameter of the pipe. So remember in the beginning of the video, I imported my entrance length data already. That's already in my Excel sheet right here. So that's why I'm leaving it as L, because that's what I imported the data as. So anyways, then you can type in this part for question number 2, and then you can get your dimensionless entrance length, which we have right here. Okay, so now what I've done is I've typed out this code right here for the velocity profile. So remember, we are finding the velocity in our system using a pitot tube. We had the pitot tube at the center line, and then we moved it down. So we had the pitot tube along the center line here, and then we moved it down. So the center line, we said that was 0 millimeters. So on your spreadsheet, this is the center line right here, this first one. Okay, so we want to find the velocity using this pitot tube. And for that, we used equation 2.11 right here. So we're just going to plug that into Matlab, which I did here. And then I'm specifying that V14 is 0. So on the spreadsheet, that's this 14th row. I'm saying that's 0 meters per second. Because really, we want to pretend that we had the pitot tube against that boundary wall, and in that case, that velocity would have the no-slip condition, and it would be 0. We didn't actually put the pitot tube against the wall because we didn't want to damage it. But we're pretending in Matlab that we did have it against the wall, so it should be 0. Okay, so that's all the code you need there, and then you can go ahead and just plot it. So what I've done here is I've broken up the plots for one graph having 2 plots and the other graph having 3 plots. So figure 3 is for a discharge coefficient for 10% and then 30%. And then figure 4 is for 50%, 70%, and 100%. And when you make these plots, you should also add a legend in here. I didn't, but you should add a legend in here so I know which color and which plot corresponds to which discharge coefficient or discharge opening. If we look at figure 3, this plot right here in blue, that's corresponding to the discharge percentage of 10%. That shows our velocity is 0. And I forgot to add the axis titles on these, but whatever. So our velocity shouldn't really be 0. It just happens to be that the data that I have here for that first run for 10%, it says that the static pressure was equal to the stagnation pressure. And that shouldn't be the case. If we look at the equation to find the velocity, we have the static head minus the stagnation head. So in my case, that difference is 0. So I have the velocity equals 0. So whoever put in this data that I have at my disposal, they inputted it incorrectly. So if you look at your data, they should be different and you should have some velocity there. So go ahead and do that. And your plots will look, similar to mine, but you'll have some velocity profile for your discharge percentage of 10%. Okay, I've also plotted the entrance length versus the fan speed here. So we already calculated the entrance length earlier on, and then I've just set up RPM and axis for the fan speed here. So we had 1250 RPM, 2000, 2800, and 3600. I divided it by 1000 just to make this axis a bit cleaner, but you don't have to do that. So this is a pretty simple plot. We have our data points, and yeah. Looks like I messed up this part though. 3, let's run it. Alright, there we go. So I accidentally put the entrance length for 4 for the 4th run 2 times. So anyways, your plot should look like this. Okay, so the last thing that we had to do was look at the volumetric flow rate and the Reynolds number. So if we go to the lab handout, that was question number 5 here. So this is the formula that we have to find the flow rate from the velocity profile. And then from that volumetric flow rate, we're going to use that to get the Reynolds number. So in Matlab, to calculate this, we're going to do this. So we're using for loops once again. So I have for I equals 1 to 5. 1 to 5 because we had 1 fan speed, and then we had 5 discharge percentages. And then here I'm starting at Q equals 0, so I'm initializing my flow rate here at 0. And then I'm doing for J equals 1 to 13. So we had 14 taps, but the way this equation is set up, we have J plus 1. So if I had J equals 1 to 14, that wouldn't have worked, because then it would be trying to go to some J value on the 15th row, and that wouldn't exist. So we're doing from J equals 1 to 13. Then you can type in this code here. That's just this formula, but kind of in a Matlab form to calculate the flow rate. If we go back here, we have Q equals Q plus, and then all of this equation that we had from the handout. So this is an update notation. So I started at Q, and I'm saying this updated Q is equal to Q plus all of this. So basically it's going to loop where we have some value, and then it will take that value here and then add on all of this stuff. And then it's going to do that from J equals 1 to 13. Okay, and then we're going to have our flow rate for, in the end, we're going to have our flow rate for each of those runs for the 5 discharge percentages, and that will be equal to our small q that we calculated up here. And then our Reynolds number, that's a lot more simple. So we're just doing 4 times the density of air times the flow rate, then divided by pi times the viscosity of the air, and then multiplied by the diameter. Now if we go down here and we plot this here, I'm doing the entrance length versus the Reynolds number. That's what we have to plot. And that's just plotting the Reynolds number on the x-axis and then our entrance length on the y-axis. So for this, I'm taking L right here. I'm taking all of the rows and then the first column. So I'm doing the first column because we had a fan speed of 1250, which is what we did in the second part of the lab here. Go back to Matlab, and then I did Reynolds number divided by 10,000, again just to make my plot look a little nicer right here. Okay, and then you should have some plot that kind of looks like this. Okay, so I'm going back just to quickly update that on this X label here, I should have had Reynolds number times 10 to the 4th, because I divided the Reynolds number by 10,000 right here. So anyways, your plot should look something like this, and then you'll be set, you'll be done with this lab.